For the opposite implication, we again argue by contradiction. This time, we assume that this limit property holds. I want to show that the set is closed, and so let's do this by contradiction. So assume the complement is not open, and this means there exists some x0 in x without a, such that x without a is not a neighborhood of x0. So what does this mean? This means there is no epsilon ball around x0 which is contained in x without a. So this means every epsilon ball around x0 so is not contained in x without a for all epsilon bigger than 0. And this is of course the same as to say that b epsilon of x0 intersects a. So this intersection is non-empty for all epsilon bigger than 0. Okay, now we want to argue via sequences because this helps us now to construct a sequence which converges to x0 and which lies in a. Namely in the following: for each n in n, we pick an element xn in the intersection of the ball of radius 1 over n around x0 intersected with a. Okay, then so this particularly means we have a sequence in a such that the distance from xn to x0 is smaller than 1 over n for all n in n. And now we see what happens. If n goes to infinity, we see that this distance, since it's non-negative, so it's bounded from here by 0. So this goes to 0, which means this goes to 0. And if this goes to 0, just as we said in the beginning for metric spaces and for convergence, this means that the sequence has to converge to x0. So then xn converges to x0. But since this is a sequence in A, so since xn lies in A for all n in n, it holds by assumption that the limit has to lie again in A. This is this time the assumption that we had. So it holds that x0, which is the limit as n to infinity xn, lies in A. But this is a contradiction since what we started with was that we took x0 in the complement of A. So there is no such x0. So this means x without A is a neighborhood of every point in it. So of every x0 in x without A. This means that x without A is open, so A is closed. This was what we wanted to show. Okay, so the closeness of a set, instead by using this awkward definition via complements, we can just characterize it via sequences. So this is the important thing to take away from this. Whenever we work in a closed set and we have a sequence that converges, we always know the limit is already is again in there. Okay, now this helps us also in giving an example for closed sets, which I haven't done explicitly yet, but sometimes you can use this sequence criterion to check this. And let me give you a very elementary example of a closed set. So we take A1, A2, B1. B2 to be real numbers, such that A1 is smaller than B1, A2 smaller than B2. And then we consider the following set, which is again a rectangle. We had before the open rectangle, so to say. Now we put R to be the product of the two compact intervals, A1, B1 and A2, B2. So this as a subset of R2. This is a rectangle geometrically. So this time we include the boundary curve, which we didn't do for this open rectangle that I had previously. So assume we now have some sequence. So we're to show R is closed. This is what we want to do. And by the previous theorem, it suffices to show if we have some convergent sequence in R, then the limit has to lie in there as well. So that xn, yn, so two components in R2, be a sequence in R, which converges in R2, but we don't know yet if the limit lies in there, which converges in R2. Okay, but as we know, this lies in this rectangle. We know that, so xn lies always in this interval, so a1 smaller than or equal to xn, smaller than or equal to b1, and a2 is smaller than or equal to yn, which is smaller than or equal to b2, and this holds for all n in n. And we know if we have a convergent sequence, so first of all, this is a convergent sequence in R2, and we have seen that the sequence in R2 converges if and only if the two sequences themselves converge. So by theorem, this was, have I written this down? 11.7. So by theorem 11.7, the sequences xn and yn, these sequences converge in R. And if we use this here, so which I call star, then we get that, and this is kind of, if the sequence is bounded, then the limit satisfies the same bounds. This is from math 1. This means that a1 is smaller than or equal to the limit of the xn smaller than b1, and a2 smaller than or equal to the limit of n to infinity yn smaller than or equal to b2. So this means the limit as n goes to infinity of xn yn, which is by that theorem nothing but the product of the two limits. We can just let them converge individually. So this is limit as n goes to infinity xn, limit as n goes to infinity yn. So this has this property, so this limit is in R, in our rectangle R. And since we started with an arbitrary sequence in R which converges somewhere in R2, and we have shown the limit is already again in R, so by the previous theorem, which was theorem 1151, R is a closed set. Okay. Now, in this section I will consider a bit more properties of closed sets and to carry out some constructions, but from this point on I will skip the proofs of these results and maybe say a bit more things about this, because this now gets very technical, and this kind of pushing around sets and playing around with them is just not that relevant for you. So these are all statements that we might need at a later point, but they are good to know for you. And so you can read up the proofs and lecture notes. They are all there in detail, and as they are very technical, it's probably also easier just to sit down, read them and think about them instead of listening to them. So it's really, don't wonder, so I will skip through the dirty details here and at what's to come. Okay, first of all, we establish some properties of closed sets, and this is now a theorem which is basically completely dual or somehow or complementary or whatever you want to call it to the corresponding result for open sets. Namely, I want to establish certain properties of closed sets that very much resemble the ones for open sets. Namely, first of all, and this is now containing a definition, so I could have made this a hybrid of theorem definition, but anyway, the so-called closed ball of radius epsilon around x0. So far we have seen open balls, but the closed ball, by which I mean the following set. I denote this by b epsilon at 0, and I put an additional bar on top of the b. So b bar epsilon of x0, this is now the set of all x in x, such that the distance from x to x0 is smaller than or equal to epsilon. So for the open balls, we always excluded the boundary, and here this just takes in the boundary of the ball. So the outside sphere, this is still contained in there. So if we add this boundary, then this closed ball is closed. So so far it's just a name, but this is really closed in the sense of what we did before. This is closed for all x0 in x and all epsilon bigger than 0. And this is basically shown by taking, by really using the definition of closeness, take the complement of this, which is just a ball removed from the metric space, and see that all around we have enough, we always have a little neighborhood. So I kind of recommend you to read up the proof of these statements a bit, because this is, somehow this is kind of giving you more intuition. So here, this is something, so at least I would really like you to read this part. Now, for the other three parts, they look similar to the corresponding statement for open sets, namely, first of all, the empty set and X themselves, itself, are closed in X. And this follows from the open set theorem, basically, because we have seen that the empty set and the whole space are open, and complements of open sets are by definition closed. And the empty set is X without X, so the complement of X, and X itself is X without the empty set. So this is just by construction, since those two sets are open, they are closed because they are kind of, in some sense dual to each other, so to say. Now, same for families here now. That if AI, I in I, if this is a family, also where I is a set, so just some family where AI is closed in X for all I. So we have this family of closed subsets. For the open sets, we knew that arbitrary unions of open sets are open again. Here it's the other way around, namely here the intersection of arbitrarily many open closed sets is again closed. And finally, before we had the intersection of finitely many open sets is open, but not infinitely many in general. Here, finite unions are closed. So A1 to AN should be some finitely many closed subsets of X. Then their union, I from 1 to N AI, is again closed in X. And the proof is actually not that hard, it's just very technical, because you just have to argue with the complements. You just apply the corresponding result for open sets to the complements, and then basically use the De Morgan rules that complements of intersections are unions and complements of unions are intersections. And they're kind of, this is why these intersections and unions basically swap places at this point. Now, so proof is in the lecture notes. Okay, now I want to introduce some additional terminology, some constructions of open and closed subsets that we can associate with sets, and give you some ideas about this, but really, as I said, skip through the proofs that are involved, because it's really more important for you at this point to get the intuition, but I really recommend you to then go through the details of the proofs when you kind of feel that you understood the basics of what these constructions are. Okay, namely, we take a metric space, X and D, and we first take an arbitrary subset of X. First of all, a point x0, which is somewhere in X, is called a boundary point of A if for all epsilon bigger than 0, we get the following. If we take, so the idea is, maybe let me draw you a diagram here, so it's just a little graph. So assume we have some set which has, so what we would expect from a boundary, assume we are in R2 and we would have some subset here, and we have some point which would, this would be the idea of our boundary. And the idea is now, to formalize this notion of boundary that we intuitively have, we say the idea is if I take an arbitrary epsilon disk, or in general ball around this point, so somewhere like this, for arbitrary epsilon, I will always get points that are in this set and points that are not in this set. So we are not inside, so it's definitely not a neighborhood of these points, but it's kind of, we have points from the complement, we have points from the set, but neither of the two is a neighborhood. That's the idea here. So for all epsilon bigger than 0, we have that B epsilon of x0 intersected with A is non-empty, and B epsilon of x0 intersected with the complement of A is non-empty. Okay, this is a boundary point. So in other words, every little neighborhood contains an element of A and an element of the complement. And the boundary of A is then just given by the set of all boundary points. So the boundary of A is the following. It's denoted by this partial symbol here. So I don't know if this is any, this is not a Greek letter or something. It's just this, usually for derivatives sometimes used. So this partial A, this is just defined as the set of boundary points. So the set of all x0 and x, such that x0 is a boundary point of A. So please note here, x0 does not have to be inside of A. So it might be outside of A, but yeah. So if we would, for example, take the set here without these, so with this boundary here removed, this would still be a boundary point of the set. Okay, this is the boundary of A. Okay, for some more terminology, I first need to erase. Using the boundary of a set, we now define two additional notions in terms of this boundary. The first one is the so-called closure of a set. The closure of A is simply defined, it's denoted by A upper bar, and this is defined by A together with the whole boundary. So the union of A and its boundary points. As I said, boundary points do not need to lie in A, so here we just take all boundary points, we add all boundary points that are not already in A. And for C is the so-called interior of a set, the interior of A. And this is denoted by A with a little ring over it. Probably the Swedish would call this or something, I don't know. But this is defined as A without all boundary points, removed. So we take points which are not in the boundary. And the idea is now, if you think about a set, and if you like intuitively here, anything which is not a boundary point should be somehow inside, meaning that the set would be a neighborhood of each of these points. And that's precisely true. So this I will fix later I will mention a remark, but this is now so far the definitions here. So before we go on, let me just give you two quick examples. I will not prove them in each and every detail, but just to give you the idea of what all these sets are. So example 1157. First of all, we stay very elementary in one dimension. Assume we have A and B real numbers with A smaller than B, and that I be defined as the interval from A to B with A included and B not. Okay, what's now the boundary points? So first of all, so what's the boundary of I? The boundary is now probably what we would explain, what we would expect to be the boundary, namely the points A and B. For A, we see that this is something we have argued before. Every open ball around A would be an open interval of the form A minus epsilon, A plus epsilon, and they all intersect I, and they all intersect the complement of I. So this means A is a boundary point. And by the same argument, every neighborhood here of B, so every epsilon ball would be an interval B minus epsilon, B plus epsilon, intersects I and intersects the complement. So the boundary is just A, B. There can be also no other points in the boundary, because for all points in the interior of the interval, so yeah, I already said, but in the open interval A, B, there we have seen we can always find some little neighborhood, there's always a neighborhood which is completely included, so a little epsilon ball which is included. And if we're somewhere outside of A and B, we can always, by a similar argument, always find a small interval which is completely contained in the complement. So no other point is a boundary point, so this is the boundary. So we can now derive what closure and interior are, and they are now what you probably expect they are. So the closure would be this semi-open interval united with the boundary points, and this gives the compact interval from A to B. And in the same way, the interior, this is, so the boundary points removed, which are A and B. B is already gone, so what we get is the open interval from A to B. Okay, so basically the simplest example. Or let's just check if you understood it. So if I would have an imaginary audience, I would now ask what's the result. If we take J to be the open interval from A to B, then what would we get? By the same argument, we would get the same boundary. So the boundary of J is also A, B, just these two values. So the closure would still be the open interval with these 2 points added, which also gives the compact interval from A to B. And now the differences for the interior, or now basically the differences in the behavior. The interior of J would now, we have seen for every point in the open interval there is some neighborhood inside. So the open, so this would mean this without the boundary points, but they are already gone, just by definition. So this is just A, B, so here the interior really equals the set J itself, which was not the case for I. Okay, let's increase the dimension and take a two-dimensional example, which is maybe also a bit more enlightening. So we consider a subset of R2 be given as follows. So A is the union of all x, y in R2 which satisfy x squared plus y squared smaller than 1, strictly smaller than 1, united with the set of all x, y in R2 for which x is non-negative and x squared plus y squared equals 1. Okay, what is this set? Let us draw a picture here. So we're in R2. So we have 1, we have -1, we have 1, and we have -1. So what are the two sets here? So this here is, if you take a look, x squared plus y squared is smaller than 1. This is equivalent to saying the Euclidean norm of x squared, of xy is smaller than 1. So this is just the circle of radius 1. So the interior, this is strictly smaller, so basically the inside of this circle here, let me try to draw this somewhat readably. Oops, yep, yeah, almost a circle, but so this here, so this open disk here, okay, and so without the boundary curve, but if we take a look on this side here, this is added. What does this mean? The square is equal to 1. This is precisely the boundary of the disk, but we only take the part of the disk which has x non-negative. So this means everything on the right-hand side of the y-axis. Here we include the boundary. Whoops. But on the one on the left-hand side we don't. This is now basically, somehow behaving similarly to this half-open intervals. Namely, here we can also see what's the boundary points of this. So the boundary points of A, so all points in which we can, if we take any epsilon disk around the point, intersects both this yellow set and its complement. So we can easily see this is just the whole boundary curve here. It consists of the boundary. So every point in here, if we take a small disk, we will intersect the complement and intersect the disk itself. Same here, with the only difference that these points are not included in the set, which doesn't matter at all. So every point here on the boundary curve would be included, meaning the boundary is the set of all x, y in R2 such that x squared plus y squared is equal to 1. Okay, and now we can just write down what closure and interior are. So the closure is, so this included, meaning this time we take the disk with all of the boundary. So here, maybe let me first write this down. xy in R squared such that x squared plus y squared is smaller than 1 united with the one where it's equal to 1, so just smaller than or equal to 1. And in the same way, the interior, we remove the boundary point, so here we remove this yellow circular line. So all xy in R2, where x squared plus y squared is strictly smaller than 1. So just to memorize, so here let me do this very small picture here. So this would be the circular line. This here would be the circle and the exterior line. So again, we would have this, whoops. So this disk width boundary. Whoops, this didn't work out well. Okay. And here we would only have the interior, so this includes the boundary curve, let me stress that. And here we would have the whole boundary removed, so yeah, somehow like this, so just schematically. Okay, so this would be boundary and closure and so on. And it's basically, it didn't matter that I took a whole semicircle, I could also just have taken some part of the boundary there. So for example, here a little bit and here a little bit or something. The boundary curves, these three sets would have been the same then for all of these configurations. So yeah, this method, so several different sets can have the same closure and the same interior. So yeah, just something to keep in mind. And I hope this was halfway illuminating. Okay, now time to collect some observations or some general abstract facts about closure and interior. Now, yeah, X is a metric space and A is a subset. First of all, to take a look at these sets. By definition of closure, interior, and so on, we have the same phenomenon that we had here. Namely, first of all, if we take, so this here is removing points from A. Maybe the boundary was not included after all, but this is we remove something or not. But what we know is that the interior is always a subset of A. And here we have at least A and might add some points if they were not in there before. So this is a subset of the closure. So these inclusions always hold. A is between its interior and its closure. Okay, the second thing is something which looks not that difficult, but this is something you would really have to prove, but I want to skip this. Namely, in the following way, the interior of a set could also be characterized as the set of all those X in A, such that A is a neighborhood of X. This is not that hard, but I recommend you to write down the proof explicitly, because this follows from the definition. I mean, if it was a boundary point, so if it was not a neighborhood, then there must be a boundary point, because we have to. There's no epsilon ball around the point, but it's completely included. So every ball must intersect the complement, which then yields the definition of a boundary point. And in a similar way, the closure is the set of all X in A, and this is something which is a bit more complicated to prove. X not in A, in X, such that there exists a sequence in A which converges to the point with limit n to infinity x n equals x. And this can be derived from this limit property of the boundary points and so on. For if x is a point in A, this is obvious because we can just take the constant sequence, duh. But if it's a boundary point which is not in A, then you can use the definition of boundary points in similar ways we did before in the previous proof there of characterizing closed sets, by constructing a sequence which converges to the point. So this is, I'll leave this up to you. So the following theorem now collects some of the properties of open and closed sets, and they are all not that difficult to prove, but I want to skip them for time reasons because it's quite technical. So we have a metric space and an arbitrary subset, a subset of X. Then closure and interior have the following properties. A, the interior of A is open in X. This basically follows from this characterization, because this is how open sets are built. B, the boundary of A and the closure of A are closed in X. So if we have this characterization and this theorem about closed sets and sequences, this is quite obvious for the closure, but for the boundary it's not that obvious. So you need to be a little careful with the boundary there. But this is also, actually the proof is not that hard. And you could characterize openness and closedness in terms of these two sets. Namely, A is open in X if and only if A equals its interior. Right? So we've seen the interior is open, it's contained in there, and the whole set is open if the set is equals the interior. And in the same way, A is closed in X if and only if A equals its closure. Okay, so proof is contained in the lecture notes. Okay, so these are some set theoretic constructions, playing around with this. What I want to do now, and this is kind of the last part of this section here, I want to generalize a notion that we used a lot in the previous semester and that we now want to also translate to metric spaces, namely limits of functions in a certain point. We have several times seen functions that were not defined in one particular point. For example, when we had differential quotients or something, they were examples of that. But this is what we want to generalize now, how we can say the function has a limit in a particular point. And this is also involves the closure at some point, but this will require some preparations at first sight. Sorry for the sudden jump. I just realized when erasing that I had made a mistake in the previous definition, so I decided to do this again. So now with a clean blackboard. So definition 1160. Assume we have two metric spaces, X and Y. And we have a subset A of X. Then A. So we take a point in the closure of A. Okay. And we assume we have a continuous function on the subset A without x0. Whenever I take a continuous function on a subset of a metric space, I consider it with the metric given by restriction of the big metric on X. So we have a continuous map from X with A without x0 to Y. Continuous. So it's not defined in x0, but kind of x0 is in the closure, so it's somehow glued to A. So this is basically what generalizes the notion of an adherent point from the previous semester. So assume we have a point in the closure. We say that f has a limit in this point. If there exists some value in y, so let's call it y0 in y, such that there is a continuous extension of f to A without, so with x0 included, such that the map f tilde is now really very analogous to what we did in the last semester, where this time we include x0 explicitly. And so the map f tilde of x is just, so it's either f of x if x is not equal to x0, or it is y0, so this new point, if x equals x0. So such that this map is continuous. Okay, so again we can kind of find a continuous map which restricts to f over over this set A without x0. Okay, then at this point, so we can insert some value here. So then y0 is called the limit of f in this point of f in x0. And we use the same notation as we did in the previous semester. We denote this by limit of, as x goes to x0, f of x. So this is now defined as this value, so this is y0. Okay, so this is how we define limits. And finally, we have, in the same way, a term that we used the previous semester as well, namely the notion of continuous extension. This is now for whole sets, so let B be a subset of X, such that B contains A and is itself contained in the closure of A. So we're just adding multiple boundary points, maybe infinitely many, but multiple boundary points. Then F tilde from, sorry, I have, I still need F, sorry. F, so in the same way as before, F from A to Y shall be continuous. So this time we just write this on A, continuous. Then a continuous map, F tilde from B to Y is called a continuous extension of F. If, and this is now in the same way as last semester, F tilde restricted to A is the same as F. So it's really a continuous map which coincides with F on the place where F was already defined. Now, these two are related, and let me clarify, these two terms are related, and let me clarify this in a remark. Remark 1161. Okay, first of all, by sequential continuity, let me just do this very quickly. We can again characterize the limit of a function by considering sequences. This is one-to-one the same as we did in the last semester. We know that the limit as x goes to 0 of f of x is a value b, if and only if, so again, same notions from the previous definition, so I don't introduce the notation again. If and only if, for all sequences xn in A, which converge to this point, so with the limit n to infinity xn equals x0, we have that the limit of the values of f also converges. So this is B. Okay, so for all sequences with which we approach this point, we get that the values also approach a certain value. And similar to previous semester here, it's also, if you want to show that the limit does not exist, this is usually the way to go, because it just suffices to find two sequences which both converge to the same point, but whose values of f do not converge to the same value there. Okay, at this point I will skip discussing an example also for this, because we have seen an example already actually. Because when I talked about continuous functions, I had these two functions which look very much the same, which were rational functions in two variables. I have basically shown that their limits exist or do not exist in a certain point. So maybe with this in mind, take a look at this example again. I don't have the number here unfortunately, but this was straight after our definition of continuous maps. Okay, part 2 of this remark. First of all, so the relation between those two is pretty obvious, I would say, because so this is, we just, to extend a given map from A to B, we just need to know that the limit exists there. And this is really an equivalence. So in this formalism, I don't introduce the notions all here again. So F has a continuous extension to B if and only if the limit of f, or other way, I need to formulate this differently, f has a limit in every point of B. So we just need to include this particular value then there everywhere, so define the extension by just taking the limits as the values of f, or the extension of f, then we get that. So this is really a direct relation between them. Okay, I just want to include one more thing into this section. This is something we probably will not need in the semester, but this is something might come in handy at some point. Namely, I want to also generalize one more notion to this setting of metric space. It's the notion of uniform continuity. If you recall, we had the notion of uniform continuity for numbers, for functions between subsets of R or C. And there we had also, the condition for that was again defined very similar to the continuity, just by taking these absolute values of differences and estimating them to be smaller than epsilon or delta or whatever. And this again, in the same way as to generalize continuity, we can take uniform continuity, straight away do precisely the same thing and generalize it. This then looks as follows. Definition 1162. Okay, now I need to write the metrics here. So x dx and y dy shall be metric spaces. Oops. Spaces, and f is a map from x to y. F is called uniformly continuous if the following holds. And maybe if you've forgotten, take a look at the old definition from the previous semester, and then you'll see that this one is precisely the same. For every epsilon bigger than 0, there exists a delta bigger than 0, such that, and now f, so we again need to compare two values of f, and we again do this by the metric. So dy of fx, f of y is smaller than epsilon for all x and y in x, with distance dx of xy smaller than delta. So here again, the same as before, uniform continuity now means this happens here for all points here. So this choice of delta, or this choice of delta is independent of the point here. So we don't, usually for continuity we fix one point, say y for example, it was a fixed point, and then we want x to be different in this way. But now here x and y can vary, so as long as they are delta close to each other, their f values must be closer than epsilon to each other. So again, independent of the point. And this is really straight away the same thing. And the reason I'm doing this is because now this has a relation to the closure and to continuous extensions, because there is a result which is the exact equivalent of a result from the previous term. Again, if we have, this time, it's okay, so let's say x and y are metric spaces. And we take a subset A of x. If a map f, which now is defined on A going to y, if this map is uniformly continuous, then there always is a continuous extension. Namely, then it has a continuous extension. So, and now I have to make precise where. So we have defined continuous extensions to some subsets of the closure, so that might extend to some points, while it might not extend to other points in the closure. But here is the good news: it has a continuous extension f tilde, which is defined on the whole closure. So it can be continuously extended to everything. So everything in the closure, there I can extend this. Okay, this is again something I will not prove here, but this is something that you might need on your journey through physics and mathematics. So let me refer you to the lecture notes, and the proof is actually not that difficult. I mean, it's very close to the original proof that we had. So just maybe take a look and study for yourself. But this is really the one of the crucial properties, and we will see another property of uniformly continuous maps in the next section. So the next section will probably be kind of, yeah, the top level abstractness that we studied. And then we will study so-called compact subsets of metric spaces. For this, we will need all the notions from this section, so, or not all of them, but yeah, almost all of them. So at least open and closed sets. So you should have really good understanding of open and closed subsets to proceed, or at least a general understanding or the general idea. Then we will use this to generalize compactness, which we so far have done. We have seen compact intervals, but the general definition is very, very delicate actually. So, but we will go through there and we will see that continuous maps on compact subsets, which we have also studied in the previous semester as for subsets of C, where compactness was just closeness and boundedness. There we saw that continuous functions on these sets had minimum and maximum and were uniformly continuous, and we will see that these properties generalize to arbitrary compact subsets of metric spaces if we find the right notion of compactness. So see you in the next section.